Good afternoon, everybody. Welcome to the Stats for the Masses webinar. Today our webinar is Back to Basics 2, Research Questions, Hypotheses, and Inference. My name is Elaine Eisenbeis. I'm the owner and principal statistician here at Omega Statistics. We did have a large number of people who registered for this presentation, and I'm seeing some re-attending with us today. So for those of you who have attended live, thank you very much for attending. Today I'm going to present a very brief overview of scientific method and how it relates to hypothesis testing. I'm going to show you how to think like a statistician when it comes to problem solving. I will give a very simple example of how to use hypothesis testing to inform your research. Today's just an overview, and I hope that the information you receive today will give you some ideas and guidance on the use of statistics in your world. As I say in every single webinar, use what you learned today and apply it in a holistic way. As a researcher, it's important for you not only to get the correct numbers, but to look at the big picture of the study and use the numbers to inform your research. The presentation will probably last about 40 to 45 minutes. Then we'll take some time at the end of the presentation to answer some questions from the audience. So I currently have muted the line, so only my voice can be heard. But Brianna's here again, and she's monitoring the chat board, so feel free to type any questions you have on the chat board, and Brianna will choose some to ask me at the end of the presentation. And if you have any technical issues, I often find that just logging out and back into the webinar clears up everything. I always say when in doubt, or probably many people say that, when in doubt, reboot. So let's go ahead and start going through the slides. This is a slide we show all the time too, just to tell you a little bit about Omega Statistics. Everybody will get a PDF of the slides, so you can look at this and see what we offer. But we help a lot of people, clinical researchers, dissertation researchers, independent researchers, anybody who's researching, we're here to help. I'd like to tell you a little bit about the Stats for the Masses webinars and newsletters. Statistics can be a difficult subject, even for seasoned researchers. Often the textbooks, classes, training programs, they make things a little bit more confusing. My goal with the Stats for the Masses series and for Omega Statistics as a company is to inform and educate about statistical concepts in layman's terms whenever I can. Sometimes that's not easy, but we try to do our best so that everyone can see the elegance and usefulness of statistics. We do have another webinar coming up in March. Actually, we have 4 of them in the Back to Basics series. This is our second. The third one we're holding in March on the 16th, and it's going to be the one for p-values and effect sizes. And I'll be sending out invitations probably in the next week or so, but you can go to our website now at www.omegastatistics.com and sign up there. It's up and ready to go for you to sign up. So in April, we're going to end with one of our favorites, which is the power analysis. Everybody wants to know how to determine their sample size. It's very important, and that is probably one of our most popular subjects. So today we're going to cover the following. It looks like a lot, but it's really not. It's basically going to be me talking the whole time. I'm not going to really run data too much. Any of the data that I did run, I've already ran it and posted it up on this PDF, or on the PowerPoint here. So we're going to do a brief history of the scientific method. We're going to see some examples of when the scientific method is useful and when it's not. There are 5 steps in hypothesis testing, depending on the source you use. Some might have 7, some might have a few more. 5 is, I like 5. And then we have the suggestions for the best test to use to address specific types of research. How to structure the study research questions accordingly. We're going to look at some tests of mean differences. I don't think we're going to do the correlation and association today, but we will look at the mean difference tests. So the history of scientific method, no one actually invented it. It developed over time. Probably the earliest person would be Aristotle, and he was the founder of empirical science, which it's a means of using observation and measurement as a part of learning about the world. Basically, you observe it and you make your conclusions, okay? But the thing that we're lacking as far as scientific method was experimentation and the ability to falsify something, falsifiability. We'll talk about that a little bit later. Experimentation is basically when you randomize your subjects and then you're going to do some kind of a intervention on one group and maybe not the other. and then come to your conclusions. That's really the most robust kind of study you can do, is an experimental study. There's all different kinds of studies, so we won't go into those today, but that's what was lacking, was the experimentation and the falsifiability. Development of a scientific process resembling the modern scientific method was developed by Muslim scholars during the golden age of Islam, and that was 10th to 14th centuries. Al-Haytham is regarded as the architect of the scientific method. His scientific method insisted upon that repeatability and replication. A study is not going to do any good or be very believable unless somebody can go out and do the same thing and see if they can try to get the same results or not. But it does need to be something that a person can replicate, or another company or whoever. It has to be replicative. Further enhancements were added by Francis Bacon, and he talked more about the experimentation and inductive reasoning. Descartes, he was a metaphysical properties person that added method via deduction. He's also the person you get to thank for those Cartesian coordinate systems with the X and Y axis and all that. And then, of course, Newton's everywhere. He first combined the theories of induction and deduction into the scientific method we use today. So what is this induction and deduction stuff? Induction, we begin with specific observations and measurements, and then we begin to detect patterns and regularities, and then we formulate some kind of tentative hypothesis that we can explore, and finally we end up developing a theory or some kind of general conclusion. And it goes from specific to general. It goes from the bottom up, is another way of looking at it. Deduction, you begin with constructing a theory. You narrow the theory into specific testable hypotheses. You collect your observations to test the hypotheses, and you use the information to make conclusions about the original theory. And that's general to specific, which is top down. People who are working on their dissertations, this is the kind that you're using, the deduction. You're kind of forming your theoretical framework and then going from that instead of the other way. These two types of reasoning can be combined into a circular type of process. It starts with the theory, tests the theory, and circles back to theory. So I'll show you a little diagram here. So here we have the inductive, which is the bottom up. So you go from your observations, patterns, hypotheses, and then have your theory. Well, the deductive, you start with your theory and work your way and confirm it. And here's your circle. So your hypotheses, you can make your predictions, you test your predictions, and so on and so on. And it's just a big circle. It goes around and around. So we should define some of our terms the way statisticians look at them: fact, theory, and hypotheses. Fact. Well, in science, a fact, typically it refers to an observation, a measurement, or other form of evidence that can be expected to occur the same way under similar circumstances. An easy one to think would be the sun rises every morning. It's just a fact. So there are some things we know that are just facts. However, scientists also use the term fact to refer to a scientific explanation that's been tested and confirmed so many times that there's no longer any compelling reason to keep testing it and keep looking for additional examples. Evolution might be one example of that. Many people will argue it is just a theory, and it is a theory. As it relates to biological development, it's been observed, tested, and confirmed so many times that it is considered a scientific fact. You would still have the creationists and such that may disagree with that. But when I mean about evolution, I'm talking more about, say, generating seeds for your garden. You know that if you pick the better ones, they're going to do better, and you take out the weaker ones, they're not going to. Your crop will get better and better if you save the better ones and you enhance the things that make those seeds strong. So talking in those terms, definitely it's been shown so many times, we accept that as fact and know that that is something that will happen. A theory, in typical use, implies a belief based strictly on observation and personal experiences of the observer. It's like a hunch. I have a theory that the sun has been rising every morning all my life, so it's going to rise again tomorrow. I'm pretty sure of that. That's my theory. But a scientist would use a theory as a conceptual framework to not only explain an observation of the sun rising every morning, because that's just a fact, but also the mechanisms behind that observation. In essence, the theory of gravity. might be something that you can derive, knowing that the sun, it might be the sun rising might be an example to support your theory of gravity, because it not only explains why the sun rises each morning, but it also the paths of the planets around the sun, tidal motion, projectile movement, things like that. So you can take that sun coming up as an example to support some theory. A hypothesis in everyday usage, it's a guess. It's not measured or confirmed. I hypothesize that my new rooster is going to crow in the morning when the sun rises. I'm such a farmer, aren't I? Anyway, I've been planting my garden a lot this week, so I guess I have that on my head. But to a scientist, a hypothesis is a working assumption. Typically, a scientist devises their hypothesis and then sees if it holds water by testing it against data or information collected from observation or from previous research. So if the test confirms the science hypothesis, it does hold water, then the scientist declares that his hypothesis can be a theory. Maybe he's deriving some theory from that. Usually, though, it's not that easy. This would be something that has to be done over a long period of time. Usually it takes more than one hypothesis test and confirmation to arrive at a generally accepted theory. This is because the scientific method must allow for that reproducibility and the falsifiability of a study's findings. So you never can be sure that if your conclusions are going to be absolute whenever you're using a scientific method. Somebody can always come along behind you, reproduce your study, and maybe come up with some different conclusions. And so you never prove anything. You just kind of lead to a general theory or general consensus. Oh, here's those two words I've been talking about, two very important aspects of the scientific method. Thanks to Karl Popper, he was a scientist philosopher, a very interesting person. Reproducibility, that means that a study must be reproducible so that other researchers can create the conditions of the study. Subsequent research must be able to collect the same type of data and perform the same set of processes as the original research. So if a person can't reproduce your study, if you don't give them enough information to as far as data collection, how it was coded, information like that, then it's going to be difficult for somebody to go out and test your same hypotheses and come up with their conclusions. Falsifiability, it's inherent in the steps of the scientific method, making use of reproducibility. It's the opportunity for the reproduced studies to negate the theories developed from reproduced studies. And what that means is that somebody could go out and do your study just like you did, and they could collect, of course, with a different sample. I mean, if they collected the same exact sample of people and did the exact same test and coding, you would get the exact same results. But if they took the same steps you did and tested it with another sample from the same population, they could always prove you wrong. They could always show different findings. So it's always that opportunity. You have to have your study has to be set up in a way that another person has the opportunity to test it and come to their own conclusions. So I've said prove a couple times, but we never prove anything using the scientific method. And that's very important because a further study may prove us wrong, right? So we might say, oh, yes, we had a significant finding on our study. Somebody else could go out and pull the sample and a different sample from the same population, but use your same steps, and they might not find significance. Okay, so to quote Albert Einstein, no amount of experimentation can ever prove me right, and a single experiment can prove me wrong. And that's what he means by that, is the reproducibility and the falsifiability. Scientific method, you think, oh, this is, we use it everywhere. No, we don't. There's many times it won't apply. It doesn't always apply. There's many phenomena and there's many situations where the scientific method just falls apart. It's not useful. Some examples I'm giving here, studies that are based on hypotheses that cannot be tested or reproduced. Well, if you can't test it, then you're not using scientific method. An example would be that much of the Big Bang theory is based on the Copernican principle, which it posits that the physics of the entire universe are arranged just like they are here on Earth. For instance, gravity is the same everywhere, it works the same everywhere. Other forces work the same on all the planets, everywhere in the universe, all galaxies. We don't know that. And nobody was there at the Big Bang to observe it. So we can come up with these ideas, we can even come up with theories, but they're not testable. Okay, so we don't know if that's correct. We're making assumptions kind of from what we know and what we think, but something could come along someday. Maybe when we start time traveling, we can find out, that maybe this falls apart, or maybe it's supported, but it's not an example of a scientific method. Hypotheses cannot be tested with an experiment. There are many people who believe in a theory of intelligent design, but we can't test. We can't test for the presence of a higher power with an experiment. We can have faith, but we can't test with an experiment. So a scientific method wouldn't apply there. And we can't use scientific method to make value judgments. Although global warming's been indicated from experimental processes, experiments have been done, observations have been made, the findings can't be used to make moral judgments, such as overwatering your lawn is evil or driving a Hummer makes you a bad person. I remember when one of my children were smaller, we saw a boy, a teenager, smoking a cigarette. And my daughter said, "Oh, he's bad." I said, "No, you can't say he's bad because he's smoking a cigarette. He's doing something that's not very smart. He's not being very bright. But that, just because he's smoking doesn't make him bad. So you can't say, you can't make those kind of judgments just because your study shows something. You can't make a moral judgment." Then there's pseudoscience. I took this definition from Dr. Lauer's website. A pseudoscience is a belief or a process which masquerades as science in an attempt to claim a legitimacy which it would not otherwise be able to achieve on its own terms. Also, fringe or alternative science, you'll hear it called that. And the most important of its defects is usually the lack of the carefully controlled and thoughtfully interpreted experiments, which provide the foundation of the natural sciences and which contribute to their advancement. And I wanted to emphasize that. Some examples of pseudoscience. There will be any number of people. I've had people call me wanting me to build a model to predict a stock market or maybe to help with lottery numbers. Trust me, if that could be done, somebody probably would have figured that out. Casinos, that's how they get by and make a lot of money because you just can't figure it out. It's a random process. So things like the stock market, lottery predictions, games of chance, you can't predict them. They're random. You can try to control it a little bit, but usually they have it set up with that random process, especially in casinos. Even if they make it so that they win 51% of the time and you win 49% of the time, it's usually enough for you to keep wanting to play, but they always win in the long run because of that random process. They just set up the game to adjust to that. And another one, you don't hear too much about it anymore, but in recent years, there was a lot of discussion about autism being caused by vaccines. That's a correlation that children who were vaccinated seemed, in some studies, to have an increased risk for autism, but that wasn't an experimental design. It was just a correlational design, so therefore you can't make that kind of conclusion. So let's get back to what we're looking at today and what it is. So statistics is the keeper of the scientific method. I love that phrase. I just feel so special. We use the theory and the tools of statistics to perform our studies according to the scientific method via hypothesis testing. And here's our steps, the 5 steps. First, you want to formulate your research questions and your statistical hypotheses to explain or test your research questions. Then you want to specify specifically what your hypotheses are. You want to choose the type of test you're going to use to collect your data and analyze it so you can test those hypotheses. So the choice of an appropriate test statistic goes along with the choice of the test you're going to use. Are you going to use a t-test? Are you going to use a regression? What kind of hypothesis, what kind of test do you need? Then you're going to compute a probability and determine if your results are significant according to the standards you've set. Usually it's the probability of 0.05 or less. Then you're going to properly state your conclusions and you're going to make inferences. And a lot of people, they'll state their conclusions, but then they kind of fall short when it comes to explaining what it might mean. So you definitely want to make your inferences. You don't want to just present your numbers and go, yep, there is a difference. Well, yeah, you want to investigate a little bit further, and I'll show you with an example at the end here, which it's a very simple example, but it'll give you an idea of how you need to have that follow through. So we want all 5 steps. So first, let's look at some basic concepts. Statisticians are very adept at being educated guessers. And I say this, anybody's been coming to the webinars for a while, I always say we're just good guessers. If we knew the truth, you wouldn't need me, right? You wouldn't have to do all this work. The scientific method helps statisticians and other researchers, of course, to make best guesses possible with the information they collect. Frequentist statisticians, which is the type of statistics we're talking about in this series, and who we basically are here, we use quite a bit. We make use of the scientific method. We assume there's no a priori knowledge of the outcomes of whatever we're studying, such that the data has to be collected and evaluated from information that we collect via a representative sample. So in last month's webinar, we talked about the random sampling. That's where this comes in. We need that representative sample so that we know we're making good guesses and we're getting a representative group that we're making those guesses on. There is also Bayesian statistics. When I was going to UCR, there was quite a disdain for each other. It seemed like the Bayesians didn't care much for the frequentists and the frequentists didn't care much for the Bayesians. I see a use for both. Bayesian statistician will allow some a priori knowledge. They'll say, well, you know, I'm making the assumption that there's going to be a certain probability that this is going to happen, and allow that, where a frequentist pretends like they know nothing until they get that sample and look at it. So the representative samples collected via random sampling, as we talked about, and that basically means that each person has an equal chance of being selected for observation in the basic form, in the most basic sense. That's what it means. There are times when a random sample can't be used, but this does not invalidate a study, but it won't allow that study to be generalizable. And I know we've talked about this before. Only studies using experimental designs are generalizable, which means that if you go out and get a convenience sample of volunteers that come in and take your survey and you do a correlation or a regression analysis on them, your conclusions will definitely matter to those people, but you can't generalize it to all the people from the population that you collected them from, because they were volunteers. They weren't randomly assigned into any kind of groups. All right, so step one, we're going to formulate our research questions and our hypotheses. So research questions should be formed after a thorough review of the knowledge base. So do your literature review. For those of you working on your dissertations, a lot of schools, they want your chapter 1 first with your introduction and your theoretical framework, which is great. But I think you should go out and do your literature review first. See what's out there, because that's going to help you form your study. You don't want to do a study that's been done 100 times before. You might find a study also that you can look at and go, oh, there's a little hole there that I'd like to patch. That's the perfect way to do it. You don't want to reinvent the wheel. You don't want a whole new theory and a whole new study, but you kind of want to expand the knowledge base, and in small ways is nice. And so always do your literature review, see what's out there. The research idea and the question should also pass the so what test, which means, will the research add to the knowledge base? Who will it benefit? Why should we care? Right? So you need to have, it has to have meaning to somebody. It has to be useful in some way. Otherwise, there's no real reason to do the research. The research question should be narrow, not broad. I know a lot of our clients that come, they have an idea for their study, and we almost always have to trim it down a little bit. For instance, what can be done to prevent domestic violence is a huge question. There's probably many things. It's too broad to be answered in one study. So you might want to make a question instead. What's the relationship between alcohol use and spousal abuse? That's more direct, and that's testable. You can test that. In the case of clinical research, the research question can be a lot easier to define in a lot of ways. For example, one we're going to look at today is the new drug. Maybe we developed a new drug, right? We're going to call it drug A. That's our treatment. Is it an improvement over drug B, which is the current standard of treatment? It's the current treatment that everybody's getting in treating depression. It's a depression drug. So we want to know if our drug, drug A, is better than the standard that's currently being used by everybody or most people to treat depression. All right, so after we develop our research question, we want to think about how we're going to find the answer to it. This is where we really need to start thinking about it. Some things to consider Or what outcome would I need to see to support my research question, and how will I measure it? The answers to these questions will be used to formulate your statistical hypotheses. You have a null hypothesis and an alternative hypothesis. In the case of our study, in our example, we want to determine if our new drug effectively treats depression. And we also want to know if it's going to do so better than the current drug. To do this, we might want to compare the depression scores between two groups of patients. The first group will take drug A, the second group will take drug B. We'll measure their depression, and we'll see if there's a significant difference between the two groups. It's not that easy. There's many more questions and concerns that you have to consider also. Who's going to be in the study? Let's say for this study, we'll recruit patients newly diagnosed with depression, and we'll recruit them from local doctors and hospitals. They're not going to be randomly selected from a population of depressed adults. So in order to have a generalizability, we can do something called randomizing, where as they come into the study, we've already figured out some kind of randomization schema, kind of like I showed you last month. And by the way, if you didn't see last month, you can go on our website and get the webinar from last month. It's free. Download it and you can look at it. And that way, when I keep referring back, you'll have an idea of what I'm talking about. But we can randomize them into groups. So we have our randomization schema that we've already built. And then as the doctors and hospitals refer them, we look at that and we go, okay, who's next on the list? What group? Okay, you go into group A. Next person goes into the group A. The next person's B, because it's not going to be A, B, A, B, A, B. It's going to be randomized, right? So you just go down the list and you assign them. That's just about as good as pulling a random sample. And in many, many trials, clinical research, that's the way it's done. So we should also set our inclusion and our exclusion criteria before recruitment so that the populations of patients is well defined, right? Do we want to look just at men? Do we want to look at men and women? Is there a certain age group? Are they going to have comorbidities? Maybe there's other things that we want to exclude for that might be causing their depression or affecting it. So those are very, very important things to think about. And then we want to know, how are we going to measure it, right? So, okay, we're going to see if they have depression and if there's differences, but how are we going to do that? Well, we're going to need to figure out a tool or an instrument to do the measuring. So usually I would choose a tool that's already been tried and true. Don't try to develop your own tool unless you absolutely have to. You can even adapt tools very often. You tweak them a little bit to fit your study with the author's permission, of course. Always get permission. But people who have designed their tools usually love to have people use them in their studies. You only have to ask and give them credit, of course. But for our study, I chose the Beck Depression Inventory. It's tried and true. It's been used a lot of times. I think it's even available online. This version has 21 items, and they assess depression on a scale of 0 to 4. And the total scores, therefore, can range anywhere from 0 to 84, with higher scores equaling greater depression. So the higher the score, the more depressed the person will be. And that's going to be our measurement. So now I go, okay, I have all that. I need to compare my two groups, and I have my tools, I have my measurements now. What test am I going to use to test my hypothesis? So depending on the type of the measurement, there can be any number of ways to set up your hypotheses. So some questions we might be asking are, will each patient receive only one of the treatments, or will all patients receive both treatments, both drugs? That would be a crossover design. Will we take baseline measurements and of depression as they come into the study, and then after treatment take another measurement, or maybe even during treatment, depending on how long the study is, you might want to take interim measurements. Okay, so we need to figure that out. Are we satisfied that randomization is going to take care of everything? Is it going to make the groups equal for group A and group B as relates to age, gender, race? It should. If you randomize them, it should. But we might want to also just control for those, or we also might want to control for some other factors. Perhaps some patients are receiving counseling, so we want to code a variable for if they're receiving counseling or not. So we can take that into consideration. There's a lot of things to think about when you're setting up your study. But for ease of presentation, we're going to say that we're going to randomize the patients who are referred to us into the two groups, and then we're going to give them the treatments for 3 months, and then have each patient take the depression inventory. Now, if I was to really do this study, I would definitely get baseline. But for this presentation. I didn't want to get that involved with the actual testing and showing the results. So we're just going to test them after the 3 months to see what their depression scores were. But you'll find out, I'll show you later, you'll see why a baseline probably would be a very good idea. Statistical hypotheses are the statements you make to test your research question, and they're worded to fit the type of measurement you will take, the tools you'll be using to take that measurement, and to suit the process of scientific methods. So you need two hypotheses. You need your null hypothesis, and your null hypothesis means no effect, and that's why it's null. This is actually the hypothesis you're testing, and this is where it confuses people because they go, well, wait, why? How come I'm not testing the alternative, which is what I want to know? Is drug A better than drug B? I want to test that. No, you're testing that drug A isn't any better than drug B. You're testing that there's no difference, okay? So there they are. There's your null, no difference, nothing going on here, and your alternative. Note that in the case of this study, we have a one-sided hypothesis because we want drug A to be better than drug B. We don't just want drug A to be different than drug B as far as the mean depression score. We want it to be better. We want the scores to be actually lower, right, for those who are taking drug A, because higher scores mean that the people have more depression. So we want drug A to be significantly lower on those scores, and that's one-sided. And as I was saying, the confusing thing for most researchers is that we're going to draw our conclusions based on that null hypothesis, not the alternative. So why is this? Well, you need to think like a statistician, and I always refer to that as I tell people, you need to think backwards. We're really good guessers, but we don't just use our intuition and observation, which is that inductive reasoning. We also use the statistical tests, and we incorporate probabilities to make our conclusions, which is the deductive reasoning. Since we're only making a guess at the truth, we must allow for the possibility of our guess being wrong. It could be false. We could maybe have pulled a bad sample. Maybe the participants didn't understand the test. I mean, it could be any number of things, but we always need to allow for the guess to be wrong. We can never be 100% in statistics about anything. As I was saying, this is due to the falsibility requirement. Somebody can come along, reproduce it with a different group of people and come up with different conclusions. They're definitely going to come up with different numbers. Now, will their conclusions be different? Perhaps. To properly test under the requirement of falsifiability, we need to test the null hypothesis rather than the alternative. So we're testing that there is no difference, and we're going to find significance and say we have significant findings if there is a difference, or in this case, if drug A performed better. Okay, so here's our null hypothesis. Whenever you're building your hypotheses, you should put in, if you're looking at means, you should mention means. If you're looking at associations or correlations, you should say so. That way you kind of give an idea of what you're testing. The mean scores of the Beck Depression Inventory will not significantly different, or they will be significantly higher for patients in Group A, because remember, higher means more depressed. So the null is covering everything but what we want, right? So the null is saying either there's no difference or, oh boy, that drug didn't work as good as the standard, right? They're more depressed. And then we're doing it when compared to the patients in control group B. So here's our alternative. That's what we want. We want to know that the mean scores of the Beck Depression Inventory will be significantly lower for the patients in group A, right? That's what we're looking for. So since we use probabilities to test our hypothesis, we're asking in essence, what's the chance of seeing that much of a difference in mean scores between Group A and Group B if the means between the groups were truly equal, right? So our probability, our test is like, well, what's the probability of seeing the differences, the means that we get? We'll do a test to see the differences and get a probability of seeing that difference. And if that probability we get from the test is lower than a value that we've set, then we can say we have significance, because that means that probability was very low that we would see something like that, those means being that different. And so I have my little caveat there. We don't know the truth, but we can use probabilities. And we can take into account the size of the sample, what we consider to be a significant difference, which is the effect size. I always ask the researchers about the effect size. How big of a difference would be significant to you as a researcher? Are you looking for a 10-point difference, 5-point difference? It matters, because the size of your effect that you're looking for is going to drive how much of a sample you need. And we're going to cover that actually next month. We'll be covering our p-values and effect sizes much more thoroughly. So given that we are asking what's the chance of seeing that much of a difference in mean scores between the groups if the means were truly equal, we have to test the null hypothesis that there isn't a difference. This way, if we get a low probability, a low p-value, this means it would be rare to see the result we find if we were to test that hypothesis with another sample using the same methods, right? So a high probability would mean the result's not rare at all. If I got a p-value of 0.7, that would mean 70% of the time I would expect to see a difference like that. But if I have a p-value of 0.03, that means 3% of the time I would expect to see a difference like that. And therefore it's rare, therefore it's significant. And here I'm talking about most tests of hypotheses are set at the 95% level. You can set it at whatever you want, but most of the time 95 is nice. It means that one would need a p-value of less than a 0.05, because that's 1. 1 is everything. 1's 100% minus the 0.95. So that's how we get that. And then if we had that value of less than 0.05, then we would say the findings were significant. That means you're allowing for a chance significance once every 20 times you perform the test. So after you decide how you're going to measure it, you need to determine what tests we're going to use. Okay, well, we're looking at means. Okay, so we want mean differences, and there's 2 groups, they're independent. Everybody's just assigned into one group. A person's either taking drug A or they're taking drug B. Nobody's taking both. So we're going to use an independent samples t-test. And there's other tests that could be used depending on the criteria, but that's what we're going to use. And we're going to make the assumption that everything we needed for a requirement to use that t-test is good. Okay, so we're going to test our null hypothesis. So we take our data, we run it through any number of statistical software programs, and then we're going to take that test statistic and compare it to a critical value. Your software program will do this for you. Long ago, you had to compute them yourself and use a table. We don't do that anymore. So for the sake of brevity, I'm going to say the critical value using a one-sided null hypothesis and a 95% level of significance. It is this value, 1.64 with the t-test. So if I have that test statistic and it's bigger than 1.64, then I know I probably have significance. And then we'll conclude that the drug taken by group A significantly improved depression over the drug taken by group B. As long as it's in the right direction, I would hope, as long as group A has a lower mean. So I ran some data. So let's look at that and perform a hypothesis test. It looks like, we had about 187 people. 80 of them were in group A, 107 in group B. Here's their means. Here's their standard deviations. These are important because equal variances, it's an assumption. The nice thing, though, about SPSS, which is where I ran this through, is it gives you Levine's test, and it'll test to see if your variances are equal between the groups. If they're not, they will give you adjusted values here for your degrees of freedom so that you can make your correct conclusions. So we actually had differences. So I'm going to use this equal variance is not assumed. And it's significant because that p-value is less than 0.05. And so we can say that there is a significant difference between the groups. So now I want to go back here. Group A had a mean of 25.9. Group B had a higher score, which means they were more depressed. So it's in the direction we want. So that's important. But what else can I see from these tests? Well, the Beck Depression Inventory was scaled from 0 to 84, right? A person could have scored a 0 where they were happy, or they could have scored a 84 where they were not happy. They were very depressed. The means of both groups were low scores, right? One was 25.9, the other mean was 30.3. That's on the lower end of that scale. So relatively speaking, they are lower, which could mean that both drugs were effective at reducing depression, couldn't it? We didn't take baselines, so we don't know how they started out. Now, if we had some very, very depressed people and we had taken the baseline scores and saw that and then looked at this and compared, we'd say, wow, boy, both of those drugs worked well, right? They both reduced, maybe one more than the other, but they both reduced. But we don't know because we didn't take the baseline. So it could also be that the patients weren't all that depressed to begin with, right? Even though they were referred for depression, we might want to go back and ask the people who referred the doctors in the hospital, what criteria did you use to refer them? Okay, so the variation in depression scores was quite different. Standard deviation, you would square this, and that would be your variance, okay? And so when you square them, they do become bigger. You can see the differences on the standard deviation. This one's twice as big of a spread as this one, just about. If we look at that, oh, I kind of already told you about that. If we looked at standard deviation, they had much more variation in group B. Unequal variances violate it, but like I said, we have that test. If that shows significance, we just look at those bottom numbers. So the difference in the mean depression scores between the two groups was indeed statistically significant. There's a 5-point difference there, 4.5. But it was only about a 4-point difference, 4.5-point difference between group A and group B. So how significant is that in application? This is called clinical significance. It might be statistically significant, but the researcher might say, well, then 5 points that's nothing, but it might be. 5 points might be everything. So don't just look at those numbers and say I have significance. Look a little bit deeper into it and see what am I really looking at here, and does it really matter? Because statistics, you could get significance. The bigger the sample size you use, the more significance you're going to see. That's just the nature of it. So you want to make sure that if you do have significance, you're following it up and really looking at it to see what you're looking at. 5-point difference might make a difference, might not. All right, so then we tie it all together. We're going to state our conclusions in reference to the null hypothesis, and here's how we say it in APA format. Okay, so group A had I think it had significantly lower mean scores than group B. Oops, that should be lower. And it's hard because whenever you have something that's scoring with higher scores mean more depression, you always think higher scores. I don't know, in my head, I always think higher scores means good, better. It's we win, It's not the other way. But a lot of times the tools higher means more of a bad thing. So, and that's what it was in this case. It's more depression. So even myself, I can mess it up. So make sure that you check that. I should have checked that a little closer myself. So this is all correct. So we are going to reject the null hypothesis. This part's correct. There is sufficient evidence to indicate that the mean scores of the Beck Depression Inventory were significantly lower for patients in Group A when compared to the patients in Group B. And I'll try to remember to change that on the handout. There's nothing worse than having a typo like that and confusing everybody. Sorry about that. All right, one final note. Never, ever accept the null hypothesis. You reject it or you fail to reject it. So you fail to reject it, but you don't accept it. And why? Because a statistician is making guesses. Really good guesses if she sets up the study and pulls the data correctly, but guesses nonetheless because of the nature of scientific method. So we may find significant differences, but another researcher may come along and replicate the study and form different or opposing conclusions. So we either fail to reject when we have no difference between the groups, or we will reject it if there is a significant difference, but we never accept it. Acceptance means we're done, we've accepted it, no more needs to be seen. That's not true with scientific method. It's never done. Well, what about the alternative hypothesis? Yeah, we also were talking about the null. Well, we didn't test the alternative. We tested the null hypothesis. What you can say about the alternative and about your and another name for the alternative hypothesis is your research hypothesis, because that's what you were testing, right? That's what you really wanted to know. So you can say that the results of your hypothesis test supported the alternative or research hypothesis if you must, but don't ever say accept. You can support it, but don't accept. Here's some references. This one was pretty interesting about why it matters to think like a statistician. I think it's important to kind of understand that scientific method and how you can relate things to it. It's very important when you're doing studies. And this is talking about how it should be taught more in schools and maybe why it's not. Probably the biggest reason, it's very hard for some people to wrap their heads around, unless you really think about it. Pseudo-Science, if you're interested in looking into that some more, there might be some Bigfoot in there, or things like that. This one I liked a lot. He thinks a lot like I do, and lies in his Lies and Stats blog. And this is a blog I liked very much. And he talked a great discussion about the scientific method and why we don't ever accept that null hypothesis. This slide has some information about what's upcoming, and I will send this to you so you can look at it at your convenience. But we're running a little bit long, so I want to get to our questions. So I'm going to bring Brianna on and see if she has some questions for us.
Okay, so we do have 2 questions while we're waiting for a response to the messages. The first one is, why do we even need a hypothesis test? If the means between the 2 groups weren't different, isn't that enough?
Oh, so you're saying to say if we just looked at the 2 groups and saw the means were different, why isn't that enough?
Yeah, why would we still need a hypothesis test?
Yeah, I mean, you could look at that and go, yeah, there's a difference, but you can't say if it's significant or not, and that's a big deal to research. It's like, well, we need to know, and that significance ties back into that probability. Let me go back up in one of these slides here, and I'll show you another reason why. Is because we are guessing, so we get these numbers here, right? They're means for the 2 groups. But we also have the standard error here, which is a measure of error because not everybody's saying the same thing, right? So everybody's scoring differently. So you have some error in the measurement. And then you have these confidence intervals down here that are computed using the standard error and could be somewhere inside the difference. So here it's saying the difference between the groups is about 4.5 points. But the true difference might be more or less than that. The true difference could be somewhere, well, let's look down here at the bottom numbers because we didn't have equal variances. But the true differences could be anywhere from -6.2 to as small as -2.6. That's making the assumption that we were going to reproduce and go out and get another sample, that we would expect that the true difference between those 2 means are going to be somewhere in there. So you can say, yeah, we have different means, but that doesn't mean anything. You want to know if it's significantly different. And that's why you need the hypothesis test, because you just want to see, wow, is this by chance that it just happened like that? Or is there something really going on here? And that's the only way you can do it, hypothesis test, and use those probabilities. It's a lot more convoluted than that, but that's one reason. Yeah, that is the reason.
Okay, great. And then our second question is, what test would you have used if your assumptions were not met for the t-test?
Oh, okay. Yeah, instead of, well, I would have went ahead and used that t-test with the equal variance assumption being violated because SPSS gave me that option. Or you can adjust the degrees of freedom. If you look back here again, should just probably just stay on that screen. If you look here, what this does is you have a little bit of a different t-test because your degrees of freedom have been adjusted. See, anytime you see this kind of number reported for degrees of freedom on a t-test, you can almost always assume that you didn't have equal variances because usually it's a whole number. And so that's what it does. It adjusts that. So I would have used that. But another test you could have used would maybe be a non-parametric test, such as a Mann-Whitney U test. And you could have done it that way, and then you don't have to worry about that. It has many fewer assumptions than a t-test. Not that a t-test has a lot, but Mann-Whitney, you can get away with different distributions. You don't have to have that normal distribution.
All right, we got one follow-up question. Why don't you just use the Mann-Whitney U instead of the t-test?
That's a very good question. I used to wonder that myself. Non-parametric techniques like the Mann-Whitney U or Kruskal-Wallis or tests like that don't have as much power. So what will happen is you could use the same sample size, find the same kind of differences, but you won't see significance because you don't have as much power with those non-parametric tests. So basically, you want to use the t-test because you have more chance of seeing significance that's truly there. You wouldn't see it as easily, and you might need to get a bigger sample. And so, it's about time and money and making the best test you can to see significance, not just to get significance, but you want to see significance that's truly there. So on the other hand, you don't want to overpower your study either because you'll see significance everywhere on the little things that don't matter. So you want it to be just right, just like Goldilocks, you just want it just right. But yeah, it would be great to use those non-parametric tests and not have to worry about these assumptions on like the t-tests and ANOVAs and such, but then you'll have to get a bigger sample basically because you don't have as much power, and that's why we use the t-test instead when we can.
Okay, great. That was all our questions.
That's it? Okay.
That's it.
All right. Well, hey, we got done on time. Thank you, everybody who attended live. I'm just so happy to see so many people came and stayed, and I will get this put together. I have a conference to go to this week, so probably it'll be early next week before you get the handouts and such. But go and sign up for the other webinars. I hope this was useful to you. If you have any questions, also, you can give me a call. I think I have it. Where am I? Oh, I guess I'm not in there. Well, you know where to find me, Elaine at omegastatistics.com. But thank you, everybody, for coming. And thank you, Brianna, for helping.
Well, thanks, Elaine.
Okay, have a good afternoon, everybody.